Okay, we're going to look at an application of using matrices to solve a system of linear equations. Now, this is a typical exam type problem, although the problem that we're going to examine is a slight twist, and it's going to look at the fundamental properties of the coefficient matrix, drawing on the idea of what's called the determinant, not like that, determinant. Maths teacher can spell. Alright, so first off, system of linear equations involves a number of equations made up of a number of unknown polynomials. So you could have two unknowns with two equations. So this could be a x and y coordinate that, and we could have two straight lines equations to represent equations for finding an xy coordinate, a point where they intercept. So of this form, here we got an unknowns of x and y, and so we can set up a pair of equations in this manner where a, b, c, d, and e, f are just parameters that constructs the straight lines, and we might want to be able to solve these simultaneously. So solving simultaneously, we could do that using substitution method. So that means maybe looking at one of the equations, transposing for y, and then substituting that into the other equation, or the elimination method. The elimination method is where we try and match the equations by having common multiples and eliminating one equation and solving for the other, or the matrix solution. So here we go. Here's a pair of simultaneous equations. They can be represented in matrix form, where A, B, C, D is what we call the coefficient matrix. Okay, coefficient matrix is generally written with an A to represent coefficient matrix. And then we've got an unknown matrix, and the unknown matrix is represented with a capital X. And at the end, what we have is called a unit matrix, and the unit matrix is some column and usually represented with a B. Okay, so we're interested in a solution to this matrix equation, and generally the solution is of this form, where it utilizes something called the inverse matrix, is what we have here. Now, inverse matrix, the inverse matrix is an important matrix that we need to be able to determine, and there's one thing in it called a determinant, and the determinant is a very important property of a matrix that we're going to examine. So let's look at an example. Here's our system of linear equations, two unknowns, two equations, and we're interested in, is there a solution? Can we solve for x and y? So set it up as, here we go, as matrix equation. There's our coefficient matrix, there's our unknown matrix, there's our unit matrix. And that's what it looks like. Let's go through the steps on how we can rearrange this equation and solve for x. So how about we multiply both sides by the inverse of A, inverse matrix of A. So multiply the left, we have inverse of A times A, and the right hand side, the inverse of A times B. It's very important that if we multiply to the left of all other matrices, then on the left hand side of the equal sign, we have to do it to the left of B on the right hand side of the equal sign. Namely because matrices have dimensions, and the dimensions of A is a 2 by 2, and the dimensions of B is a 2 by 1. So if I'm multiplying matrices, I want to make sure that my dimensions are going to fit together. And this order, 2 by 2 multiplied by 2 by 1, we can see that the two inside dimensions match, and so that means matrix multiplication is possible. Would matrix multiplication be possible if we multiplied this way? B multiplied by the inverse of A. We would see that the dimensions will clash, and so matrix multiplication would not be possible. So having multiplied both sides by the inverse of A, we're going to see that some matrix multiplied by its inverse will give us the identity matrix. And the identity matrix multiplied by the unknown matrix just gives you your unknown matrix. So there's our solution. Now, here is our information for our inverse matrix. And what we have here is AD minus BC. That little bit at the bottom is what we call the determinant. And we use a det of A. Det of matrix A as the notation to represent the determinant. Okay, so let's apply this to our situation here. So there's our solution for the unknown matrix, the inverse of the coefficient matrix multiplied by the unit matrix, like we have here. Rub that out because we can't see it after I've coloured it all in. Rub, 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 rub. Okay. Then if I go ahead and work out that inverse using my rule, I've got my determinant in the bottom, 4 minus negative 9, which is positive. And then there's my inverse matrix. And we're going to see that performing the matrix multiplication and multiplying by this fraction, we get a real solution, a real unique solution for x and y. And geometrically, that is what we're going to call our point of intersect between our two straight lines. Point of intersect between our two straight lines. Alright. System of linear equations don't have to be small. They can get bigger. 3 by 3, 4 by 4, 5 by 5. Each time we need to have 3 unknowns, 1, 2, 3, x, y, z. And if we've got 3 unknowns, we must have 3 equations made up of those 3 unknowns. And that allows us to end up with a square coefficient matrix, which can be determined to have an inverse matrix, and so a solution will exist. We get our 3 by 3 coefficient matrix here from our 3 equations and our 3 unknown parameters. And so here's our solution. Take the inverse of the coefficient matrix multiplied by the unit matrix. Now this 3 by 3 matrix, the inverse, is not a rule, is not a thing we can work out by hand. Not maybe in math methods, Kaz. Perhaps in future math studies you might learn how to work out the inverse matrix of a 3 by 3, but for now we're going to do that using Kaz only. Okay? Only Kaz. It's not part of our course to learn how to do it by hand. And it's simple to do it in Kaz. You set up this matrix and put to the power of -1, hit enter, and you'll have it complete for you. Try it. Now, let's examine a typical exam problem. These are usually multiple choice, but on our SAC coming up in a couple of weeks, there will be a question very similar to this that you would have to work out by hand and give me a solution with working out. So a simultaneous linear equation, and have a look, we've got unknown parameters as coefficients. So we need to find A that is a real constant, such that our simultaneous linear equations have infinite many solutions. Infinitely many solutions. I wonder, what does that mean? I know an equation could have one solution because that could be where two straight lines intersect. But how can they have an infinitely many solutions? Well, there's some options. A could be some real numbers, all real numbers perhaps, maybe. Or it could be all real numbers except two possible numbers. Or it could be just those two possible numbers. Let's see how we can come about determining which is the correct answer. First off, what does it mean for an equation to have infinite many solutions? Consider it as the two straight lines cross at every single point along the line. And if two lines are crossing at every single point along itself, well, I think it means that they kind of overlap each other. And we have every point along this line being a point where they intersect. So in other words, the two lines are the same line. Now, let's consider that. First off, let's take our system of linear equations and rearrange them, and we're going to make y the subject. And we're going to end up with two linear equations, and they're the gradients. Alright, straight lines, they intersect at the origin like that. Now, for it to have infinite many solutions, they intersect at every point along the line, that is, they are the same line. So let's see that. That means I want to find the value for A, such that the gradient of both lines gives the lines being the exact same gradient, being the exact same line, having infinitely many solutions. So the fundamental question is, what values of A cause the linear equations to be the same line? This is our approach. And this is where the matrix equation form of the equations come in. The matrix approach is very powerful. It gives us something, useful tool to find the possible values of a parameter very quickly. What kind of tool do you think that is? Something about a matrix, a property about the matrix, other than Keanu Reeves being a tool, a property about the matrix that allows us to figure out something about the system of linear equations. There it is, matrix equation. What about this 2 by 2 matrix that's going to help us figure out what A should be? The main property that causes straight lines to become the same line, have infinite many solutions, is the gradients of the line. So the gradients are made up of this coefficient matrix, and so the coefficient matrix controls the gradients of those lines, and in fact the determinant. The determinant is the property we're after. It is the mechanism that determines what solutions can be achieved. Can we achieve one unique solution, or can we achieve no solution at all, or can we achieve infinitely many solutions? There's 3 options there. I'm going to discuss each of the 3. So let's have a look. If the determinant of the coefficient matrix A is 0, then there exists infinitely many solutions. So that's the first fact that we're going to identify, and I want you to write that down in your book, highlight it, put a big bubble around it, just like this. And if the determinant of the coefficient matrix is 0, we've got infinite many solutions, and that means the equations are the same line. So let's do a little calculation and see how that works out. So let's take the determinant of A. So we go AD minus B times C. A times a plus 1, minus 3 times 2, which is 6. Okay, let's expand the brackets. A squared plus a minus 6 is 0. That's factorized because it's a quadratic, and we see that we get a plus 3 as one factor, a minus 2 is the other factor. So therefore, a is negative 3 and a is 2. And there's our possible answer. When a has those values, then our straight lines have the same gradients. And that means they are the same line. So there's your determinant rule. AD minus BC for 2 by 2 matrix with the elements A, B, C, D. Basically, the determinant, it determines if the matrix equation is solvable. Are we going to end up with a solution if we try and work out the inverse matrix and then multiply the inverse matrix by the unit matrix and try and solve for the unknown matrix? If it is solvable, then the solution is possible, and what type of solutions are we get? So let's look at the 3 options that we're going to have. So one option is when the determinant is 0. So when the determinant of the coefficient matrix is 0, then we say that matrix A is singular, and its inverse, a to the power of neg 1, does not exist. Okay, it's not going to exist because we're going to end up with, let's have a look at the equation for an inverse matrix. There's the inverse matrix rule. There's the determinant, AD minus BC. So if that is 0 there, we're going to have 1 divide 0, and 1 divide 0 is undefined. That means a to the power of neg 1 will not exist, regardless of what the elements inside the matrix is. Okay, so generally that is one key indicator whether we're going to have infinitely many solutions or no solutions. And there are 2 possibilities that can arise from the determinant of A is equal to 0. The matrix equation has infinite many solutions. That means 2 straight lines are the same, just like that, one over the other. Or we can have the matrix equations have no real solutions, and that occurs when straight lines are parallel. They have the same gradient but different y-axis intercepts. Same gradient but different y-axis intercepts. They are parallel. Okay. Alternatively, what about the situation when the determinant of A does not equal to 0? It has some real number. The coefficient of matrix, the coefficient matrix A, then will have an inverse, a to the power of neg 1, an inverse that exists, and that the matrix equation will then have a unique solution. And that means the 2 straight lines are going to intersect. You're going to have an intersection point just like that. And this is the xy values that we're trying to work out. So 3 options: infinitely many solutions, or no solutions at all, or one unique solution. Okay, let's look at this question. Simultaneous linear equations given by that, where k is a real constant, have a unique solution, provided that these are our 5 options for the values for k. Now, we want a unique solution. A unique solution. So that means we need to use the idea when that of A cannot equal 0, and when the det of A does not equal to 0, then we're going to obtain a unique solution. So we first set up our coefficient matrix, call it matrix A, taking the coefficients 1, 2, 3, 4, and we work out the determinant of A times D minus B times C. We set up a quadratic equation. We simplify it a little bit by dividing by -1. Then I'm going to factorize. And we'll see that it factorizes nicely into these two factors. So that means k cannot equal to -5 and k cannot equal to 3. And so it's not allowed to equal those numbers. That means k is allowed to equal to every other real number except -5 and 3. And when that happens, we're going to end up with unique solutions. So, look, there's a very important thing to note about the situation when the determinant is equal to 0. That gives us two possibilities: no real solutions or infinitely many solutions. So which option would it be if we get that situation? If the values of the unknown parameter produces for us two equations that are identical, then there are infinite many solutions. Otherwise, they are parallel lines and there is no real solution. So if we work out what the value is for the unknown parameter, we're going to substitute that back into the equations. And we want to check then to see if we're going to end up with two equations that are the same. And if that happens, we've got infinite many solutions. So determine the values of m such that the simultaneous linear equations, that one, and notice now we have a parameter here at the end, the y-intercept number, that's what it's responsible for. It depends on m. So solution is first set up. We're going to set up our coefficient matrix. We're going to work out the determinant of the coefficient matrix. Like that. A times D minus B times C. We're going to make it equal to 0 because that's when we have infinite many solutions. Expand the double brackets, then simplify a little bit, and we're going to see that we can only continue to factorize if we complete the square. So completing the square gives us that. Minus 16 there, add the 16 to the other side, gives us that one. Square root both sides, square root of 16 is positive or -4. And then we add the 2 to the other side, so we get a positive 2. Two options, m equals 6 or m equals -2. Which one is going to give us the possibility of infinite many solutions? Which one is going to give us the possibility of no real solutions? So let's try m equals -2. Then if we substitute that back into our original equations, we're going to see that we're going to have two lines that are in fact parallel. Same gradients. When we add the x terms to the other side, divide by 5, we're going to end up with the same gradient. But the y-intercept is going to be different. Otherwise, when m equals 6, the equations become this. And we're going to see if we simplify these equations, divide both sides by 5, we get x plus y equals 1.4. And second one, divide both sides by 3, we get x plus 1 is equal to 1.4. The same equation. That means we have infinitely many solutions. And m must equal to 6. And we're finished. Very good.